In today's lesson, we're going to continue our study of continuous random variables. And in particular, what we're going to talk about today is how the expected value and the CDF, though we have already talked a little bit about the CDF in the last lesson, how those concepts generalize to the case of continuous random variables. So with today's lessons, we want to understand how the CDF and the PDF are related. And we saw that when we introduced the PDF, but we're going to explore that a little bit deeper here. We want to understand how concepts from the discrete random variables case, so expectations, variance, that type of thing, are able to translate to the continuous random variable case. And we also want to understand percentiles and how those relate to continuous distributions. So we saw them with respect to samples, and now we want to see them in the population. So the thing that I want to point out a little bit, and again, this was briefly touched on during our last lesson, but I'll make it explicit here, is that when we're dealing with continuous variables, we're really thinking about it as the limiting case of discrete variables, right? And so if you think about when you were learning integration, right, you would have seen pictures like this, where we said with an integral, we want to estimate the area under a curve. And so you can draw in these rectangles and then add up the areas of these rectangles. And as you make your rectangles smaller and smaller and smaller, you're getting closer and closer to the true area, right? And so in the limit, the summation of those rectangles becomes what we know as an integral now. Right? And in the case of probability distributions, we're thinking about the same thing, right? If you think about making the bins that the discrete variables can fall in smaller and smaller and smaller, or you think about when we were running that timer and we went to 3 decimal points, right? So if you break those 3 decimal points and you add a fourth one, right? And so you make your 1,000 bins become 10,000 bins, right? And you keep doing this further and further and further. You're making those groupings smaller and smaller. And eventually you'll get to rectangles that have no width, right? In the limit there. And then we've moved from discrete variables to continuous variables. And so all of this is to say that essentially what we're going to be doing in the continuous case is taking anything that we saw as a summation and making it into an integral. And just about everything else is going to hold steady from what we saw before. And so really a lot of this is going to be a way of reviewing the concepts that we saw in the discrete case. And I'd say that the main important distinction to make is that we have to always keep in mind that our density function, that the PDF, is not giving us probabilities of events, right? That's where the continuous and the discrete case differ from one another, and it's an important distinction. But when we're actually thinking about learning these concepts, really if you replace your summation with an integral, you're probably going to be well on your way to understanding what's going on. So this is just sort of putting to words that point I was making. So if we replace the summation in the discrete setting with an equivalent integral, we can derive the same quantities. So if we want to do the expected value, we know that the expected value is the summation over all possible values of x times the PMF. So what we do is we say the expected value of x is going to be the integral over the whole line of x times by the density, right? And so it's sort of that exact analogy. If we want to take the expected value of a function, then we plug in the function into the integral, right? And we're going to be able to interpret these quantities in exactly the same way that we did in the discrete case, right? They're exactly analogous. And when we're computing them, they're computed exactly analogously, right? So not only can we get sort of a functional representation, we can also get the variance, right? And so the variance is going to be the integral of x minus the expected value of x all squared times by the density, right? And so all of these things translate exactly the way you'd expect them to. We already saw that when we were deriving the PDF, we can get the CDF by integrating from negative infinity up to x, right? And we sort of use that as the way that we defined the PDF, but of course that holds in exactly an analogous way as well. And then the fundamental theorem of calculus is sort of what connects those two quantities together. Now, we've previously discussed, and I've re-emphasized over and over, that any singleton has a probability of 0 for continuous random variables. However, we can integrate to get the probabilities of events. So if we wanted to know the probability that x was larger than some threshold a, the first thing to note is that because the probability that x equals a is 0, whether we use strict inequalities or inequalities that contain the equality, then we'll have the same probability, right? The probability that x is greater than or equal to a is the same thing as the probability that x is greater than a, because the probability that x equals a is 0, right? And so both of these quantities can be written as the integral from a to infinity of our density, which is the same thing as 1 minus our CDF. So in general, when we're dealing with continuous random variables, we do not need to be careful about inequalities. We do need to be careful in the discrete case, where the probability that x is greater than or equal to a is not necessarily the same thing as the probability that x is greater than a. But as a general rule, we don't need to be careful for continuous variables. Now, when we were looking at our data sets, we generalized the concept of our median to that of percentiles. And we said that the pth percentile of a data set was the value at which p% of the data fell below that value, and 1 minus p% fell above that value. And so we could think about doing the same thing with distributions, and it's a lot easier to think about in the continuous case. So generally speaking, we can find the population value for these using the continuous distribution. With the discrete distribution, it's a little bit harder to do. So if we define eta of p to be the 100th percentile, so eta of 0.5 is going to be the 50th percentile, or the median, right? Then basically what we want to do is we want to solve for p equals f of x of eta of p, right? And so if we think about what we're saying here, eta of p is going to be the pth percentile. So p% of the data have to fall below it. So if we plug in p equals 0.25, we're saying we want 25% of the data to fall below this, or we want the value that if you put it into the CDF gives you 0.25. This is the same thing as integrating from negative infinity up to eta of p of our density function, right? And so we could use this here to start actually solving for the different percentiles. It sort of involves inverting our CDF function here. So if we were to find eta of 0.5, then we get the median. The median is also known as the 50th percentile. In summary, if we replace summations from what we saw in the discrete case with integrals, we're going to get sort of the corresponding quantities. We can do this for the expectation, the variance, the CDF, and they sort of translate exactly. We also saw how we can use that sort of integration to find percentiles by solving that integral equality. And once we're dealing with sort of explicit densities, we'll be able to solve for those sort of more explicitly. So in the next lectures, we'll continue our study of continuous random variables, and I hope to see you all in those lessons.